How have car engines gone from this to this? We now live in an era where a car you can buy as a punter has an engine that creates 2,000 horsepower. In this video, we'll be looking at all the main jumps in performance right from the beginning that have got car engines to where they are today. Considering that the first ever car had less than 1 horsepower, what has been the journey to create 2,000 times more power from what is fundamentally still an internal combustion engine? To start with, let's go back to the origin of the car engine. Internal combustion itself was invented in the 1700s after the steam engine had come along and revolutionised the creation of doing work, an energy multiplier that would change the world forever through sparking the Industrial Revolution. A steam engine is classed as external combustion, and multiple inventors were quickly converging on a more efficient solution that could contain the energy transfer, allowing as little as possible to be wasted, escaping into the surroundings. In 1794, Robert Street patented the first internal combustion engine that used liquid petroleum. Jump to 1807 and you have the first internal combustion powered four-wheeled vehicle, a simple wagon that drove 100 metres a few years later, but using hydrogen and oxygen, not quite the car and engine that we'd think of. Finally, someone bagged a patent. In 1853, a couple of Italians managed to get the first patent for an internal combustion engine. It was called obtaining motive power from the explosion of gases. In the late 1800s, however, it was the Germans that went nuts with this technology. Nikolaus Otto, alongside Wilhelm Maybach and Gottlieb Daimler, came up with this patent called the compression-charged 4-stroke engine cycle. Essentially, the same rough engine cycle that has been used to power most car engines since. So, 4 strokes: intake, compression, combustion, exhaust, suck, squeeze, bang, blow. Here's what those 4 strokes can sound like. The Otto cycle, as it was named, was a game changer, and it was used to power what is classed as the first ever production car, the Benz patent Motorwagen. Invented in 1885, this thing was the genesis of the passenger car as we know it. It was petrol-powered, using a single-cylinder 4-stroke engine. It may have had 3 wheels and looked a bit more like a tricycle than anything properly motorised, with its steel-spoked wheels and solid rubber tyres, but this thing was considered the first practical, modern automobile and the first to be put into series production. Its very specific power output from its 1-litre engine was 0.74 horsepower, or 0.55 kilowatts, from a single cylinder that was mounted horizontally and read to 400 RPM. In terms of torque, we are talking 0.59 pounds-feet, less than you could generate with a flex of your ankle, but let's not judge, it was a start. Some parts of that engine are recognisable to us. The fact it has a cylinder, a piston, and a pushrod actuated exhaust valve. But then there's stuff like the open crankcase, the drip oil system, and the fact that the fueling is done by fuel-soaked fibres. It's all done via evaporation. That is quite alien to us. So we come to our first real jump into the future of horsepower, and this was Carl Benz iterating his own engine design by implementing something called a carburetor. The early evaporation technique for fueling lacked any real control over the air and fuel mixture entering the engine, which really affected the drivability of the car. This early carb design united the air and fuel mixture in a much more cohesive fashion. Suddenly, the supply of air and fuel to our 4-stroke engine cycle was much more reliable and consistent, which led to a massive increase in power to 2 horsepower. Horsepower jump number 2, having multiple cylinders. In 1895, we have this thing, the Buffum 4-cylinder Stanhope, which, as stated, had the first ever production four-cylinder car engine. Now, multiple cylinder engines had existed in industry beforehand. They were massive things, but they still had the same fundamentals. They had to calculate crankshaft balancing and having numerous con rods attaching to that crank. With those calculations done, those could be applied straight to a much smaller engine to go in a car. Some further engine balancing later and you have a layout that has so much more potential for creating power, spreading the load over 4 pistons and cylinders, and it was a much more balanced layout than the Benz, thanks to the outer pistons counteracting the reciprocation and unwanted vibrations from the other two. That in turn means you can turn up the wick further without worrying about the engine wanting to shake itself apart. It had individually cast pistons which had their own individual cylinder heads, but the pistons were all acting on a common crank. Another technology that was very much in its infancy that featured on this engine was overhead valves. Instead of having an inlet and an outlet on the side of the cylinder, these were overhead, and that technology has endured for over 100 years and is very much still going. By multiplying up to 4 cylinders, we had our power increase, somewhere between 6 and 20 horsepower. Sources seem to differ online depending on where you look. But no matter what, that's either a 3 times, if not 10 times increase in horsepower by having 4 cylinders. Horsepower jump 2.5, even more cylinders. Someone had the clever idea of putting 2 4-cylinder engines onto a common crank, creating the first ever V8. Rolls-Royce were the first to it, creating a limited run of V8 engine cars, but really the first mass-produced V8 was built by Cadillac. In 1914, they came out with the Type 51, which had a 5.1 litre V8. More cylinders means more displacement, which means more air in, which means more fuel in, which means more power. That 5.1 litre V8 put out 70 horsepower. We're getting there. Horsepower jump number 3, supercharging. In 1921, Mercedes were the first company to supercharge one of their cars. The supercharger itself was invented in 1878 by a Scotsman called Dougal Clerk, but it was our man, Gottlieb Daimler, that developed what would become known as the Roots supercharger. In 1921, Mercedes attached one of them to one of their road cars. The Mercedes 4-cylinder engine, non-supercharged, created 25 horsepower, but when boosted by a supercharger, it created 38 horsepower. That is a 50% increase, and so was born the Mercedes compressor badge that has lasted all the way up into the 90s and 2000s. At this point, carburetors were still the best solution to get that ideal air-fuel ratio to maximize power and fuel efficiency. But then World War II came along and moved the needle significantly. Horsepower jump number 4. While Spitfires and Hurricanes were all using carburetors to fuel their V12s, the Luftwaffe changed tack to mechanical fuel injection for their Messerschmitt 109s. Instead of fuel being sucked into the airstream, it was instead being injected under high pressure via nozzles into the combustion chamber. It was a much more powerful and fuel-efficient way to run a Messerschmitt's V12 Daimler-Benz engine. It's funny how those names keep popping up in the history of the internal combustion engine. Of course, it was the Germans that took the tech and plumbed it into a car with the 1951 Goliath GP700 using a Bosch mechanical fuel injection system in its 2-stroke engine. More relevant to this story, it was 1954 when mechanical fuel injection made it to a 4-stroke engine in the legendary Mercedes 300 SL. At this point, let's take stock of where we're at in terms of power levels. In 1954, we've got the 300 SL as peak car, and it has multiple cylinders, straight 6. It has a mechanical fuel injection system and has overhead cams, although that technology has been around for a while now. The mechanical fuel injection took the Merc engine from 175 horsepower to 240. And with all this new speed and power, another technology had to be added in, a dry sump lubrication system. There's no point in creating all of that power if your engine is then going to be oil starved. So by bringing in a dry sump system, you could control the lubrication of that straight six and keep it going, which was great, especially in racing. Horsepower jump number 5. Never mind mechanical fuel injection, that was so 1954. By 1958, we had electronic fuel injection. Mechanical fuel injection distributed its fuel based on the throttle pedal connected to a fuel metering valve. That was a very agricultural way to go about it. Electronic fuel injection used sensors, particularly a manifold absolute pressure or MAP sensor. It took that value combined with air temperature, engine speed, and other values from other sensors around the car to come up with a much more accurate air-fuel mixture. Suddenly, engines became much more clever. Electronic fuel injection was first conceptualized in the USA by Chrysler, but it was unreliable and the tech was sold to and then perfected by, guess who? The Germans. Bosch brought out the Jetronic system in the 1960s, and that was used all the way to 1975, finishing with the V12 Jaguar XJS. Yet again, EFI offered improved performance, better fuel efficiency, and lower emissions through being able to control fueling much more precisely via sensors and a computer, the Engine Control Unit, or ECU. An EFI system could now automatically adjust the air-fuel mixture to different conditions, leading to better engine response, a more stable idle, and easier starting in various weather. Horsepower jump number 6, and this one is another biggie. The 1980s brought about one of the most important jumps in the search for more horsepower. Our dads discovered the turbocharger. Superchargers had existed for quite a while now, but they had that one major drawback. They used up engine horsepower to spool up. Turbochargers changed that by using exhaust gases to spin up a small turbine, recycling the energy that up until now an internal combustion didn't use. It wasted it, it let it out into the surroundings. Those exhaust gases are rerouted through the turbocharger and then preferably through an intercooler to cool down that air, condense it so you can fit more of it into the engine cylinders to create more power. No longer were engines relying on atmospheric pressure to create their power. In the 80s, engines were gulping in air. Add in a shitload of fuel and you have some serious horsepower gains. From the late 50s to the late 70s, power outputs had only been slightly increasing thanks to bigger displacements and more cylinders. Lamborghini's V12 was putting out 440 horsepower, but was totally obliterated thanks to turbo boost. To find the first turbocharged production car, you actually have to go back to 1962, where you'll find the Oldsmobile Cutlass Jetfire. The aviation industry had been using turbos for a while, but they were far too big and cumbersome to fit to a car yet. But by the 1960s, that technology had been refined and shrunk down to the point where it could fit underneath a bonnet.
And the turbocharger whirls at incredible speed, packing the fuel mix into the engine. Result, compression zooming upward, and that enormous surge of jet fire power.
It never caught on in the States initially after the Oldsmobile. It was more over here in Europe that the turbo revolution hit home. BMW, Porsche and Saab bloody loved the things, cementing the 80s as the decade of the turbo. Combined with ECUs getting cleverer every year, engineers could really crank up the boost and optimise the timing of an engine to send power through the roof, pushing their engines by getting closer and closer to the dreaded knock limit. With 2 banks of cylinders on offer in some engine layouts, and therefore 2 exhaust manifolds, twin turbochargers became the craze. F40, 959, a lot of the Group B monsters. If you wanted to compete with the best, you needed turbos. We started the decade with 440 horsepower, but we were now ending it with 600 in the epic Venturi W8 twin turbo, the most powerful car of the 80s. It was in the 90s that the real duel between natural aspiration and turbocharging really kicked off, because the McLaren F1 came along with no turbos and became the fastest car in the world. It had its amazing 6.1 litre naturally aspirated V12, but outside of that, it was still mostly turbos. The XC220, EB110 and 911 GT1 packed 2, if not 4 turbochargers, which meant 500 horsepower from factory was now an absolute piss in the park. Natural aspiration still had its place though, with variable valve timing getting cleverer by the year, compression ratios could be increased, and materials and electronics were developing at a rate where engineers could push their engines harder and rev them higher to still create good power. That made room for the McLaren F1, CLK GTR, Ferrari F50 and Cerebra Speed 12 to create serious power, still naturally aspirated. Turbos were great, but some of the engineering hadn't been 100% thought through. Engines were overheating due to cooling system development not keeping up at the same rate, and blocks were cracking, head gaskets blowing, and internal components bending. The hunt for easy horsepower in the 90s came at a cost. Then the Japanese car manufacturers weighed in and taught the rest of the world a thing or two about how to create big power from an engine without blowing itself apart. The Nissan Skyline GTR and Mark IV Toyota Supra taught us Europeans, Americans, everyone else in the world how to thoroughly over-engineer an engine. They brought to the table closed head blocks, parallel turbochargers with ceramic bearings to dissipate heat more, sodium-filled valves, forged conrods, forged crankshafts. Suddenly, the rest of the world had a lot of catching up to do. Into the 2000s, manufacturers were staying naturally aspirated, almost bucking against the heavily turbocharged 80s and 90s. If you think about the F430, Ford GT, Carrera GT, Enzo, Murcielago, Gallardo, they all used displacement and the latest ECU tech to create somewhere between 450 and 650 horsepower. So no real jump versus the previous couple of decades, until the big boy came along. Horsepower jump number 7. This was the combination of big displacement, numerous turbochargers, and the financial grunt of one of the biggest automotive companies in the world. I'm of course talking about the 1,000 horsepower Bugatti Veyron. This Volkswagen Skunk Works project was concocted by the legendary Dr. Ferdinand Piëch, and when it came out with its 1,000 horsepower output, it was a genuine step change in production car engine performance. It simply blew everything else into the weeds. It was the ultimate top trumps card. It blew our minds. It went about it by combining 8 litres of displacement with 4 turbochargers. Those 4 turbos were initially all the same size, but as the W16 was developed, it switched to sequential turbochargers, 2 small ones and 2 big ones, to maximise performance at low revs and allow that engine to head up towards 1,500 horsepower from a production car. In the Veyron era of the mid to late noughties, we thought we'd peaked, and I guess in terms of purely internal combustion engine performance, we kind of did for a while. Yes, the hybrid Holy Trinity came along as the next level of car performance, but their engines never matched the Veyron. They needed electrification to make up the gap to 1,000 horsepower. If we take 2005 as that 1,000 horsepower Veyron benchmark, let's go through the engine technology developments that have happened since then. Let's start with twin scroll turbos. Turbos before just had one inlet for those exhaust gases, but twin scrolls have 2. That means they're less susceptible to exhaust pulses and have much more consistent boost. That means turbo lag is reduced and torque is increased. Nikasil is used a lot now in cylinder liners to reduce internal friction. That means your piston is having to work that bit less to move up and down the cylinder, creating a more efficient powertrain. Improvements in materials have created a massive shift as well. Steel is now making a bit of a comeback because it can now be made to be super lightweight, but also strong. It's now taking back over from titanium. That's something that Koenigsegg are doing right now, especially with their crankshafts. Manufacturing in general has improved. Manufacturers like BMW are taking a lot more care now with their cylinder heads. Before, they would cast a cylinder head and there'd be lots of scraggy leftover bits of cast metal that they would just leave for an engine tuner to go in future and port and machine a head to get it flowing better. Now, BMW are doing that from factory, going in and machining, porting the heads to make sure that airflow is maximised and there's more potential for power. Good job, BMW. Electric turbochargers are now a massive deal. Porsche has taken inspiration from F1 and has developed these electric turbos that spool up ridiculously quickly, almost making engine response as good as a naturally aspirated engine. To dive deeper into how engines have developed in the last 20 or so years, I grabbed Riccardo Breda. He's the chief engineer at a place called Italtecnica. It's a fascinating facility. Let's hear what he's got to say on the matter. So if I think back to what I would say was like the Top Gear heyday, so say like 2010, a lot of supercars were 500, 600, it was only really Bugatti that had a 1,000 horsepower engine back then.
Yeah.
What has moved on technologically between, say, 2010 and now that allows engines like this to exist?
I think, first of all, the simulations of the fluidodynamic of the engines, because nowadays with modern computer power, you can simulate much better the behavior of the engine. Then you have also, talking about electronics, you have like engine control. So, for example, knock control and strategies for cutting the power when the engine is at its limit.
So that didn't exist back in 2010?
It existed, of course,
right?
But it was not so sophisticated.
Okay.
Nowadays, you can go up to knock limit, let's say, and keep the engine there as you want. Okay. And also, of course, all the technology has improved in everything, turbochargers, internal components. And then also the expectation of people is going up and up, because, yes, 15 years ago, the most powerful car had 1,000 horsepower, the Bugatti Veyron. And I also can remember that when I was in middle school, I saw Bugatti Veyron, 1,000 horsepower.
Yeah.
They finally made it to 1,000, let's say.
This could be double.
Yeah.
Two Veyrons worth sitting there.
Yeah.
Insane.
Also, what is more important now, I think, is in efficiency of the engines. Because nowadays, with the regulations, it's very difficult to go up in power, pure power. But the target now is to go up in power by keeping the engine very efficient and very environmental friendly.
Well, that's what's mad. Like, so 7-litre quad turbo V12, and it's Euro 6 and US compliant.
Yeah, it will be.
How? Yes. I mean, it must be what, cylinder deactivation? Like, how are you managing it with that engine?
No, we have no cylinder deactivation. No? But as I said before, the engine control strategies are what manage to reach that kind of levels in nowadays. Also, if you see OEM cars nowadays go with crazy powers by being Euro 6 compliant, US compliant, because of strategies in the pollutant emissions test. For example, one of the most difficult tests is the cold start for engines. One of the most demanding with the pollutants, because when you start with freezing temperatures, you have to put a lot of fuel inside the engine. Catalytic converters are not working. So good strategies to reach as fast as possible the target for pollutants will allow you to meet the pollutant emissions.
Well, I've spoken to engineers that were at Cosworth doing the Valkyrie engine, and also the AMG1 guys, and their main focus was preheating
the catalytic converters.
Otherwise, they would miss the emission goal by a mile. With
that is
engines.
The most difficult part of the emission test, the cold start. Yeah.
there might be stuff you can't tell us, but what's next? V16, flat 16, flat 12, you're halfway there.
Yeah.
But what's the next project?
Depending on the customers that come, so we can do everything.
Okay.
Yeah.
So if someone comes to you saying, okay, we want a V6, V8, V12, V16, V10, you'll be like, cool, we'll do that.
Yeah.
And how long would you say it takes from customer saying, we want a quad turbo V12? How long is the gestation period there until you've got this?
From white paper to this build, I would say a couple of years.
Wow, okay.
From scratch to this, yes. This was particularly complex, let's say, but if it's easier engine, like 4-cylinder V6 or something like that, maybe 1.5 years. Also, yes. Also, maybe less, depends on resources put in, but yeah.
Well, it's been amazing coming here. Thank you for having us. Next time, I'll come. I'll take you out for dinner, you know.
Okay.
Nice wine. If we've got a 3-cylinder, single turbo.
No, make 4-cylinder, not 3.
No, it's cool. Right, Ricardo, thank you.
Thank you very much.
Awesome. Ricardo is an absolute dude, and we had an amazing day filming with Italtecnica's quad turbo V12. If you haven't checked that video out, definitely do so after this. The 2,000 horsepower Giamaro V12 brings us to where we are right now in 2025. In the face of electrification, a chunk of the performance car market is heading in the complete opposite direction. The Aston Martin Valkyrie is kicking ass with its 11,000 RPM V12, Bugatti are coming out with a V16 soon, Red Bull is building a 4.5 litre V10 for its hypercar, and Hennessy have got their 300 mile an hour contender too. What these all have in common is displacement and either revs or heavy turbocharging, sometimes both, with materials and electronic control over the chemistry of combustion being pushed to their current limits. What makes them even more special is that they all have to meet strict modern emission standards, all while creating 1,000 horsepower plus. The most important key to that is heating the catalytic converters from cold. Maybe we can get onto that in a future video. That was the journey from less than 1 horsepower to where we are today, heading towards 2,000. I love internal combustion engines, and despite what the news may say, I reckon they've got a long life ahead of them. Do they need to go past 2,000 horsepower? No. Will they? Almost certainly yes. Let the road to 3,000 horsepower commence. Thank you for watching this video, it means a lot to me, and if you enjoyed it, I'd really appreciate it if you subscribed to my new channel. What's for you won't go by you. I'll see you in the next one.